Let's start off with what is a limit? A limit is simply the y value that our function is approaching at a certain x value. So a limit is a y value. That's really all you need to know at this point. Let's talk about notation and how to write limits. We have two different types of limits. We have one-sided limits and an overall limit. One-sided limits can either be from the left or from the right. And these are what those one-sided limits look like using calculus notation. We read this as the limit as x approaches a from the left of f of x. And we read this in a similar fashion, the limit as x approaches a from the right of f of x. A couple things here. I use lowercase cursive. This is LIM. You do not have to make the L like this, but we do normally see limit notation with a lowercase l. And then this arrow here means approaches. We see that this little, it's not an exponent, but that's where it is located. This is a negative symbol for left or a subtraction sign, however you want to look at it. And this is a plus sign for from the right. Now, A, what is A? A is simply an x value. We will be replacing A with just any x value like 3 or -7 or 0, whatever. This just represents an x value. Now the overall limit looks very similar, except it just doesn't have a little minus or plus. And we'll talk about how the left and right limits determine whether or not the overall limit exists or not. So the overall limit we simply say is the limit as x approaches a of f of x. Now I wrote f of x here because that's the particular function I have on this page. The function could be named something else, as we know, maybe g of x, or you might actually have the function written out here. Now that we've been exposed to the limit notation, let's take a look at actually evaluating some limits graphically. We can see here that we have this function g, or g of x, and we can see that this function, even though we don't know that much about this topic yet in calculus, we can see that this function is continuous. It looks like everywhere, except here when x is 1. We clearly have an issue here. We'll learn later that this is called a removable discontinuity. However, let's take a look at the left-sided limits as we approach 1 and the right-sided limit as we approach 1. So our left-sided limit as we approach 1 from the left. So on our function, approaching 1, here's the line x equals 1, and we want to approach that on our function from the left. So we're going to be coming this way. We're going to be coming this way. As we get really, really close to when x is 1, what is our y value approaching? So we can do this with an arrow. We can clearly see that our y value is approaching a little bit greater than 4. I would say maybe like 4.2. So even though our function is not defined there, there's an open hole, the limit is all about what y value we're approaching, and that y value is 4.2. This is not a perfect science. I'll put a little approximation symbol there instead, just because I'm estimating. And then our right-sided limit, as we approach x equals 1 from the right, would look like this. We can see that it's still also 4.2. Note that from the left and the right, our function is approaching the same y value as we get closer and closer to when x is 1 here. So we would say also that our right-sided limit, as x approaches 1 from the right, is also 4.2. I do need to point out that because both the left and right-sided limits exist and are the same, that means that the overall limit exists. So I'm going to put in conclusion here, or coming to a sort of conclusion, or thus, x approaches 1, the overall limit of our function g of x is going to be 4.2. Because both the left and right-sided limits exist and are the same number. Now, it is worth also pointing out that if we actually plug in 1, not just get close to it, what is g of 1? Well, it's not 4.2. The coordinate point 1 comma 4.2 does not exist on this function. Instead, g of 1 is right here, the y value when x is exactly 1. See, limits talk about approaching the x value and getting real close to it, but this means the exact value of y when x is 1. And that would be, again, we're going to estimate a little bit, I would say 1.8. So the limit exists, the overall limit exists as we approach 1 because the left and right limits exist and are the same. Therefore, our overall limit is the same. However, our function value is different. So limits are getting very, very close, and it's what y value we approach, whereas this notation, this function evaluation, or the function at this exact point, is exact. Go ahead and try this problem here. Go ahead and pause your screen and see if you can figure out both the left and right limits as x approaches 3. Well, here are our two one-sided limits. I drew the vertical line here. This is the line, as we recall, x equals 3. So we can approach x equals 3, which is the x value we care about here. We can approach that on our function from the left and from the right. Note that clearly they're not going to be the same because we're not approaching the same y value like we were in the previous example. As we approach 3 from the left, our function g is getting very, very close to the y value of 4. So again, limits are y values, and it's the y value that our function approaches. Then as we approach 3 from the right, so approaching x is 3 on our function from the right, we're approaching the y value of -3. Yes, we actually hit it, but the limit doesn't care if this circle is open or closed. The right-sided limit here is going to be -3 because that's the y value we're approaching down here. So even though our two one-sided limits exist, because they are not the same, our overall limit as x approaches 3 of our function, we say does not exist, DNE. It doesn't exist because the left and right-sided limits don't agree. Using a little bit of calculus notation here, and I just wrote this out. Your book talks about this as well, but they might not use the exact same lettering, but that's okay. So for any function f of x, the overall limit as x approaches some a value of our function is L, okay, L is the limit, if and only if, IFF. So again, the overall limit is equal to some number L, if and only if these two things occur. Ready? The left limit is L, and the right limit is L. So in our previous example, well, 2 examples ago, actually, our left and right limits were both the same thing. They were both 4.2. That meant that our overall limit was 4.2. However, in just the previous example, we saw that our left limit and right limit both didn't equal the same thing. Therefore, our overall limit didn't exist. So again, if this is not the case, if our left and right limits either don't exist or are not the same, we say that the overall limit does not exist, DNE. I'm going to end the video with this quick example. We can see that this is a rational function, f of x. I know it's rational because there's a vertical asymptote in here. So this is a rational function that has been shifted, it looks like 6 units to the right. Let's just take a look at what the one-sided limits are at our point that we care about, which would be at x is 6. Anywhere else on this function, we're fine. You know, the limits exist, we're continuous, like there's no issues. But at x is 6, we can clearly see we have a problem. This again is called a vertical asymptote. And in calculus, we call that an infinite discontinuity. And we will talk about that shortly. But let's take a look at our right-sided limit. So, or our left-sided limit rather, as x approaches 6 from the left of our function f of x, and then we'll take a look at the right-sided limit as well, the limit as x approaches 6 from the right of our function. Let's see what these are. So from the left, our function is clearly going up, 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 up. It's never going to hit x equals 6, but it can get real close. 5.9, 5.999, 5.99999. They keep getting, the y values keep getting higher and higher. So we say that our left-sided limit is positive infinity. For positive numbers, we know we don't need the little plus in front, but you can put it there if you want. Then as we approach 6 from the right, coming from the right of 6, x values greater than 6, look at where our y values are going. So when x is 6.01, 6.001, 6.0, we can see that our y values are going down, down, down towards, you guessed it, negative infinity. Now, it is completely fine to allow one-sided limits to equal infinity or negative infinity. This is mathematically okay to say. However, we would not say that an overall limit goes to infinity. It's just kind of one of those weird math rules that not everybody technically agrees on. Either way, these don't agree. So our overall limit as x approaches 6 does not exist.